Welcome to A-Level and AP Physics. In today's lesson, we will discuss standard model. We will discuss how this theory explains the whole universe. And also in explanation, we will discuss what are fermions, what are bosons, and what are the fundamental particles, and what is fundamental particle. Then we will also discuss how we can classify matter and antimatter. Means we will discuss about hadrons, leptons. Then we will also discuss about baryons and mesons. So all these concepts we will cover in today's lesson, and this lesson is very important to understand standard model. We will also discuss some tricks how to remember the charge on different quarks with some very simple classification. At the end of the video, we will also do some past paper questions so you can understand how to answer questions about standard model. And today's class we will discuss question number 40 from October-November 2020 paper 1-2. First of all, let's try to understand what is standard model and what this model is explaining. Means how this model is explaining the universe and everything inside the universe. So there are two main things explained by this model. The first thing is that what the universe is. Means what the universe is made of. This we can explain with the help of standard model. It also tells us what is holding everything in this universe together, even including us. How atoms and quarks in our body, they are hold together. So these things are explained with the help of standard model. According to standard model, everything in the universe is made of matter particles, is made of fermions, and everything in the universe is held together by bosons, and bosons are force carrier particles. So we can write down here what are the bosons. They are force carrier particle. Each force has its own boson, force carrier particles. We will discuss later more about bosons. First of all, let's try to understand what are fermions. Fermions, they consist of quarks, means they are classified into two classes, quarks and leptons. If you look at the number of quarks, we can see here we have two quarks here. Again we have two quarks plus two quarks, and again we have two quarks, so plus these two quarks. So we have total 6 quarks, means 6 quarks in total. So we can write down here 6 quarks in total. Now if you look at leptons, we have 2 leptons here. If you look at this one, this is electron. Electron has its electron neutrino. So these are 2 leptons. If you look at the next one, we have muon. This is lepton, but muon also have its own neutrino, and that neutrino is called muon neutrino. Now if you look at the next one, we have tau lepton, but it also has its own neutrino, and that is called tau neutrino. So all these leptons, they are 6 in total. So very important point to understand is that electron, it has its own electron neutrino. We have muon lepton, it has its own muon neutrino. We have tau, and tau has its own tau neutrino. So the leptons, they are also 6 in total. Now one more thing we need to understand, it's a very common at AS level. We need to understand what is the charge on the quarks. The charge on the quarks mean if you look at these 3 quarks, if you look at up quark, jump quark and top quark, they have the same charge, and the charge on them is equal to 2/3 of the charge on electron. Means these 3 quarks, they have the same charge. But if you look at these 3 quarks, means down quark, strain quark and bottom quark, all of them, they also have the same charge, but charge is equal to one third of the charge on single electron. This is very important concept. You need to understand. Up means something higher. Charm is also something is higher, and top something higher. All of them, they have the same charge, so the charge is higher. Down, something is low. Strange, something also sounds like different than other things, kind of not good. Bottom, low also, so they have lower charge. So all these three quarks, they have charge minus 1 by 3e, means one third of the charge on electron. Now let's try to understand a little bit about these bosons. So you can see we have this first boson. This is photon, and this boson is responsible for electromagnetic force. We can simply say is responsible for EM force. If you look at the next two bosons, we have Z boson and W boson. W boson also have two types. So one is W minus, W negative, and W plus. So Z and W plus, W minus, they are responsible for weak nuclear force. We can simply write down here weak nuclear force. So the bosons responsible for weak nuclear force are Z boson, W plus and W minus. The next one, gluon. This boson is responsible for strong nuclear force. Strong nuclear force. And the last one, actually, in theory we call is graviton. That is not written here because it's still not discovered. Is graviton, responsible for gravity. So this is for gravity. Higgs boson we will not discuss at this moment because this is just beyond the scope of AS level. Let's try to understand what is fundamental particle. Fundamental particle simply means that it cannot be broken into smaller particles. So we can simply write down cannot be divided, cannot be further subdivided. Subdivided means it cannot be divided into smaller particles. You can also say it cannot be broken into smaller particles. So those are fundamental particles. So what are the examples of fundamental particles? So the examples of fundamental particles are quarks. So all these 6 quarks, they are fundamental particles. So we can write down the examples of fundamental particles are quarks, and also we can write down the examples of fundamental particles are leptons as well. Means all these 6 leptons, they are fundamental particles. We cannot divide them into smaller parts. We also need to understand leptons can exist individually, means they are individual particles, so they exist individually. Very important point, we have to be clear. They exist individually, means they are individual particles. But even quarks, they are fundamental particles, but they do not exist individually. They make other particles, but they do not exist individually. So they do not exist individually. Very important. But if we talk about AS physics, at that level, if they ask you what are the examples of fundamental particles, you can say is electron, you can say muon, you can say tau, electron, neutrino, muon, neutrino, or you can say tau, neutrino. All of them, they are fundamental particles. But quarks, they are fundamental particles, but they do not exist individually. Now let's try to understand how we can classify matter into different classes. Matter can be classified into 2 main classes. First class is hadrons. We can classify into hadrons, and we can classify matter into leptons. Hadrons, these are heavier particles. We can, as you can see from H, these are heavier particles, so we can also write down heavier particles. On the other hand, leptons, they are lighter particles, meaning the mass is less. So these are lighter particles. Now let's try to understand what is main difference between hadrons and leptons, not just based on the mass. Hadrons, actually, they feel strong nuclear force, means they experience strong nuclear force. They feel strong nuclear force, or simply we can say they experience strong nuclear force. On the other hand, leptons do not experience strong nuclear force, or simply we can say do not feel strong nuclear force. So this is one fundamental difference between leptons and hadrons. One is the mass, the second is based on strong nuclear force. Hadrons we can further classify into two more classes. Hadrons we can classify into baryons. And also we can classify into mesons. Let me write down some examples of leptons. We have discussed a lot about leptons, but if you are not still clear about examples of leptons, so the best example can be electron. Electron is lepton, and electron neutrino, this is also lepton. So we can write down here electron neutrino. So this is example of lepton, electron neutrino. Mesons. Baryons consist of 3 quarks, means one baryon has 3 quarks. This is the composition of baryons. On the other hand, mesons, they consist of quarks and antiquark, means one quark plus one antiquark, they make one meson. So we can write down quark and antiquark. Now let's try to understand what are the examples of baryons. So the best example of baryons is proton, means very easy to understand at AS level. And proton, we understand, consists of 2 up quarks and it consists of 1 down quark. So this is the composition of proton, and proton is a baryon because it has 3 quarks. Neutron is also baryon, and neutron consists of 3 quarks. Neutron consists of 1 up quark and it consists of 2 down quarks. So this is composition of neutron, and neutron is baryon. Now let's try to look at example of mesons. There are many examples of mesons. We will just look at negatively charged kaon. So let me write down here. Negatively charged, it means the charge on kaon is negative. We can write down negatively charged kaon. Very long name, but simply you can understand with this example, negatively charged. So this bar on the right side, it means this is telling you the charge on this particle. So this is negatively charged kaon. And if you look at the composition of this one, kaon consists of 1 strained quark, so this is quark, and it consists of 1 up antiquark. So this is 1 up antiquark. So this is up antiquark. If you look at these two bars, this bar is to the right. It is telling us the charge. But this bar is on the top. This is telling us this is antiquark. So this is very important. You need to understand the difference as well. Now, what is the charge on this one? If we find the charge on kaon, we understand charge is -1, but you can find the charge with the help of these quarks. The charge on strained quark is -1/3 of the charge on electron, but the charge on quark means on up quark is plus 2 by 3, but now this is anti quark, so this is minus 2 by 3e. If we add these two together, so the total charge on kaon, this is minus 1. So this is also, you can find out the charge on any particle if you have clear understanding of quark composition. Means if the quark composition is given to you, you can find the charge on any particle. Let's look at example of proton. Try to find out the charge on proton. Before I explain you how to find the charge on proton, let me also explain to you little bit about particle and antiparticle, means the quark or antiquark, we can also say particle. For example, quark is one particle, so this is up quark. Let's say the example of up quark, so this is particle, so this is up quark. And antiparticle of this one is up antiquark, means the antiparticle of the quark is up antiquark, so this is up antiquark. So let me write on here up antiquark. So what is the symbol for this one? So the symbol for this one is U, but there is a bar at the top, and the symbol for up quark means this is over up quark. The symbol for this one is simple U. Now what is the charge on up quark? So these are particle and antiparticle, or matter and antimatter, so they have opposite charge. If charge on up quark is plus 2 by 3, means 2/3 of the charge on electron, so the charge on up antiquark, this is negative 2 by 3 of the charge on electron. So it means particle and antiparticle, they have opposite charge if they are charged particle. If they will have opposite charge if they are charged particle. If they don't have charge, so there will be no opposite, so they have opposite charge. So this is very important. If particles are charged particle, then particle and antiparticle, they will have opposite charge. So this is very important point you need to understand. Now let's try to find out the charge on proton. So let me write down here. Proton, it has 2 up quark, it has 1 down quark, and the charge on up quark is plus 2 by 3e. So we just need to add all these charges together, and the charge on down quark is 1 by 3. So if we add them together, so we will get plus e. So this is how you can find the charge on proton. The same process you can use for neutron as well. So let me rewrite here neutron. If you look at quark composition of neutron, neutron has 1 up quark, it has 2 down quark, and the charge on 1 up quark is plus 2 by 3e, and the charge on 1 down quark is minus 1 by 3e, and the charge on 1 down quark again we can write on it. If we add all of them, our final answer will be 0. It means neutron has no charge. So this is what we need to understand about matter, how we classify matter. Next we will look at antimatter. Now let's try to understand how we can classify antimatter. Antimatter can be classified into two classes based on the mass. The first class we can say is antihadron, so we can classify into antihadrons, and we can classify into anti-leptons. So we can write down here anti-leptons. Antihadrons, as it is here, hadron, it means heavier particles, so these are heavier particles. As you can see here, L is here. You can easily remember that these are lighter particles, so these are lighter particles. But antihadrons can be further classified into two classes. We can classify into anti-baryons, so we can write down here anti-baryons, and we can classify into anti-mesons. Again, baryons, they consist of 3 antiquarks. Only difference is they consist of 3 anti-quarks, means each quark become anti-quark. But on other hand, anti-mesons, they consist of quark and anti-quark, means quark become anti-quark become quark. Again, we can simply say they consist of quark and anti-quark. So this is composition of anti-mesons, quark and anti-quark. So there are two in total. Let's look at examples of anti-baryons. As we have already discussed, proton is a baryon, but if we look at anti-baryon, means anti-proton, anti-proton is an example of anti-baryon. So anti-proton, proton has two up quarks and it has one down quark, but now it is anti-proton, so every quark it becomes anti-quark. So simply we need to add these bars at the top. Now if we look at anti-neutron, anti-neutrons means this is also anti-baryon. So the composition of neutron is one up quark and two down quarks. But now this is anti-neutron, so each quark become anti-quark. So simply you need to add these bars. If you look at the charge on proton is +1, but the charge on antiproton, means the charge will be equal to -1. But the charge on antineutron is still 0 because neutron is not charged particle. Let's try to look at example of anti-mesons. We have already discussed negatively charged kaon. The antiparticle of negatively charged kaon is positively charged kaon. We have discussed that negatively charged kaon consists of one strained quark and consists of one anti-up quark. But now if you look at the quark composition of positively charged kaon, so we have strange quark. This is a quark here, so this become anti-quark, and anti-quark here, this become quark. So now if you look at the charge of kaon, so the charge on anti-strained quark, this is 1/3 of the charge on electron, and the charge on up quark, this is 2/3 of the charge on electron. So its total charge is +1e. So they are particle and antiparticle. So if we say this is our meson, if this is our meson, so this is an example of anti-meson. So this is how you can understand the difference between meson and anti-mesons. Let's try to understand some examples of anti-leptons. The best example of anti-lepton is anti-electron, because electron is a lepton, and anti-electron, this is anti-lepton, anti-electron. But anti-electron, we also call it as a special name. It is called positron, and the symbol we use for positron is E+. Plus is simply telling us the charge on positron is positive, but the charge on electron is negative. So that's reason for electron, the symbol we use for electron, this is here. So this negative sign bar is telling us the charge on electron is negative. And also this is a special symbol for antiparticle of electron. So electron and positron, electron is a particle, positron is antiparticle. So they have opposite charges. Another example of anti-leptons can be anti-neutrino. So we have three different types of neutrinos. So this is anti-neutrino. You can also give examples of, let's say, you can say is electron anti-neutrino. So we can write down electron anti-neutrino. So let me write here. So this is electron anti-neutrino. Now we need to understand for neutrino, let me write down here. The symbol is also very important. For neutrino, the symbol we use is, for neutrino means electron neutrino. The symbol we use, this is electron neutrino, E for electron. So this is electron neutrino. Now if I talk about electron anti-neutrino, you need to understand how to write the symbol and how to identify the symbol. So simply first you need to write down electron neutrino, then you simply need to add this small bar at the top. So this is telling us this is electron anti-neutrino. So this is all what you need to understand about standard model. If you have this understanding, you can answer questions at S level. This question is asking us which particle is hadron. If you look at the first one, electron, we have discussed that electron is lepton, so this is not over possible answer. Now if we look at the second one, neutrino, neutrino is also lepton, so this is also not correct option. But if we go to third one, positron, this is antiparticle of electron. So let me write down here, this is antiparticle of electron. Electron is lepton, positron, electron is lepton, so positron, simply we can say this is anti-lepton, so this is not hadron. So this option is also not correct. Our answer has to be D now because we just left one option. Let's look at proton now. We have discussed about hadron and leptons. Hadrons are heavier particles, and hadrons can be classified into two classes. We have discussed baryons. We have also discussed about mesons. In the last slide, we have discussed that examples of baryons are protons and neutrons. These are examples of baryons. But baryons and mesons, they belongs to hadron family. So this is our right answer. So proton is also hadron. So this is hadron. So our answer is D.